All right, so what we're investigating here is we want to determine the amount of work done on an object, okay? Now, we've been doing that for a week and a half already. Essentially, there's two ways to calculate work. Work is what? It's a change in kinetic or potential energy, or a change in mechanical energy, okay? It's a change in mechanical energy. That's what work is. Is there another way to calculate work? But another formula. Right, F times D, force times distance. Okay, looking at the setup of this lab, we're going to have a rubber band, a meter stick, and a spring scale that measures force. Which way would probably be most appropriate to calculate work in this lab? If I have a meter stick and something that measures force. Force times distance. Okay, just making sure you're all awake. I know it's Monday morning. Okay, all right, so we're probably going to be using that for this lab. Now, the way we set this up, okay, and you got to be listening carefully here if you're going to kind of get the hints, because I'm not just going to go, hey, today the manipulated variable is, okay, you're going to have to listen to the to how the experiment's going to work. Okay, what we're going to be doing is stretching this rubber band between the legs of two desks. Okay, you actually have to have two different desks, because if you use just one desk, they won't stretch that far. Okay, so we're going to put it between the legs of two desks, as you see in the diagram here. Okay, the maximum distance apart that these desk legs should be is 10 centimeters. That's the maximum. Okay, basically, you just want it so that this rubber band is taut. Okay, just so it's not hanging loose. Okay, you want those desk legs far enough apart that it's just taut, and there's enough room to put a meter stick in between. Everybody follow there? Okay, so 10 centimeters is the max. We found that the groups that had them at 10 centimeters started to struggle near the end to get quality data, right? So I would say probably around 8 centimeters is probably the magic number, okay, for the distance between the legs. But essentially, guys, you want the rubber band to look something like this, okay, when it's all set up, about that tight, not like this, and not hanging loose. Everybody follow there? All right. So what we're going to do with the meter stick, okay, we're going to choose some distances. And then we are going to stretch the rubber band to those distances and record the responding force that it takes to stretch them there. Okay, that's what the spring scale is for. The spring scale will measure the force, okay, that is used to stretch the rubber band to the distances that we are choosing. One of the things that you have to make sure does not change during this lab, because it will really mess up the data and you'll have to start over again, is how far apart the legs of the desks are. If that changes at any point, it will change the amount of tension in the rubber band, and that will interfere with the rest of the trials after that point. Okay, so your smallest group size here is going to be 4 people, because you need 2 people to do the most important job in this lab. It's also the easiest job in this lab, but it's the most important. They have to sit in the desks and make sure that they don't move. Oh, you called that, okay. See, they have to sit in the desks and make sure that they don't move. That means no wiggling in the desk. So if you got a person who's like really jittery or just had a big giant Red Bull or whatever, okay, they should not be the person sitting in the desk, because the desk will vibrate and it'll move. Okay, they need to be someone who's calm, cool, and collected and will not move the desks. Okay, so they sit in those desks, and the other 2 people will do all the pulling and measuring and all of that kind of stuff. Everyone follow there. Okay, but it is absolutely crucial that the distance between those table legs does not change. What if your rubber band breaks in the middle of the lab? You got to restart. Okay, we had no rubber bands break this morning. Just inspect your rubber band, okay, before you start. The first one I pulled out this morning had a chunk out of it. Okay, and that's just a manufacturing problem. Okay, it just had a chunk taken out of it, and as soon as I went like this, it snapped. Okay, so just check to make sure your rubber band doesn't have any flaws before you put it on there. Okay, because if it does break in the middle, okay, you have to get another one. They're all supposed to be about the same, but they're not. Okay, they're not all the same. Otherwise, everyone would get exactly the same data when they do this lab, and they don't. Okay, so just make sure that, give it a couple trial stretches, make sure it doesn't break before you wrap it around the table legs. When you wrap it around the table legs, okay, or the desk legs, sorry, the spot you want to wrap it around is where the leg becomes the foot. Okay, so there's the shaft here that is the leg of the desk, and then at the bottom there's the little pivoting feet, okay, that kind of keep the desk level. The rubber band should sit in the space between the shaft and the foot. Okay, so on both desks it should be in that little dip in. Okay, so it doesn't show it on this diagram because theirs looks a little bit different. So you've got the shaft of the desk, okay, it comes to a point there, and then there's a little ball joint that actually sits up inside of here that allows that foot, okay, which is kind of triangular. So the rubber band needs to go right in there. I know I'm a terrible artist, but you get the idea, right? Okay, so that's where they need to be, is in that part of the desk. Okay. When you have it set up, okay, the ruler, the meter stick, should be, so if I'm looking at this from a top view, okay, here's the two sides of the rubber band, okay, the meter stick should be right in between them, right? Because when you hook on the hook from the spring scale, okay, they're going to be together. Yes, your group's going to have to tell you what to do. Okay, now, you can see here that also in the diagram, they have pulled both sides of the rubber band. You have to do that. Okay, if you pull only one side of the rubber band, the results are a lot different, and you tend to very quickly pull the elastic band beyond its true elastic range. Okay, a rubber band has an elastic range where it's true and linear. That is, the further you pull it, okay, the more force you require. Then there's this point where it stops being linear, okay, where you just have to put tons and tons of force to stretch it, and it's really not stretching anymore. It's just permanently deforming the rubber band. Okay, we don't want to get to that point, so that's why we're setting the maximum distance as like 8 centimeters between the legs, so that we don't get to the point where we're just deforming the rubber band. Okay, everyone follow there? Okay, so that should help you there with the design, the manipulated, responding, and controlled variables. I've mentioned a few things there. Okay, you guys should be able to figure it out because I essentially still gave it to you if you were listening really carefully. Okay, now the hypothesis. Okay, we want to generate a hypothesis that explains how we can calculate the work done in an object. Okay, but we want an if, and then statement. So in the if part, okay, you should probably tell me what work is. Okay, I mean, if we're going to have a hypothesis that talks about calculating work, we should probably first say what we think work really is. Okay, the and part, as always, describes the experiment. Okay, so just a quick description of what's going on. Okay, the kinds of things you're measuring and stuff like that. Okay, in the then part, okay, how are you going to calculate work in this experiment? And we kind of said that earlier. All right. Now, in the procedure here, I've listed distances of 5, 10, 15, and 20 centimeters. I got new rubber bands this time. They don't stretch as far as when I made up those distances. Okay, so the new distances are here. Okay, and it has to be in meters. Okay, we have to have our distances in meters here, otherwise we don't get the right units when we do our work calculation. All right, so our distances are 0.02 meters, that's 2 centimeters, 0.04 meters, that's 4 centimeters, 0.06, 0.08, 0.1, and 0.12. Okay, so 10 and 12 centimeters at the end. Any further than that, and we're well beyond the elastic range of these rubber bands. All right, so we have chosen the distances now, okay? They're in there, they're set, okay? We need to see what forces are required for each of those distances. Okay, it's just going up by 2 until you get the chart full. Okay, that's basically what you're doing. Okay, starting at 0.02. Could we also have 0 and 0 in here? We could. I don't have them written in here because I want to have as much data as possible. But when you do your graph in Google Sheets, okay, you should include 0, 0 as your first point, because obviously when the rubber band is not stretched, it doesn't require any force either. Okay. All right. So those are the distances we're going to pull to, okay? And when you're doing the measuring, make sure that the person, this is why you need 4 people in your group. One person's just going to pull, okay? Make sure that you're looking from above, because if you're looking at an angle, it distorts what you think is the actual distance that's pulled. Okay, so make sure that when you're looking down on the rubber band as you pull it. Okay, everyone follow there. All right, there is one problem with these spring scales. All right, when we moved to this school in 2006, Mr. Dickey and I did all the equipment ordering for physics, and we ordered spring scales that measured force, that have newtons on them. And we were really excited when they came because the boxes show a picture of a spring scale with newtons on it. Problem is the spring scales inside the box don't have newtons on them. They have grams and ounces. So, well, we call the company up and say, send us the wrong stuff, blah, blah, blah. Like, no, we sent you the right stuff. Look at the box. We're like, we don't have any problem with the box. The box is wonderful. The stuff inside's crap. Okay? They wouldn't refund our money, so we've never ordered from them again. See? Customer's always right. Okay? Or you stop buying from that person. Okay, your economy lesson is now over. Okay, so what you need to do is convert the grams to newtons. That's a super, super easy calculation. Okay, all you have to do is take the number of newtons, the number of grams, and divide it by 100, and you've got the number of newtons. Okay, so whatever it reads on the spring scale, divide it by 100, and you've got your newtons. Okay, so if it says 400 grams, that's 4 newtons. It's not exactly that, but that's the easiest way to do it. It's actually supposed to be 98.1, but dividing by 100 you can do in your head, okay, and that'll still work for us. Okay, so take whatever it reads in grams, divide it by 100, and you've got your force in newtons. Everyone okay with that? All right. Now, when you get to the analysis, when you get to the point where you have all of your data collected, then you're going to build a Google Sheet where you're going to graph this stuff. Okay, spoiler alert, this is what the graph should look like. But obviously neater because Google Sheets will make it nicer than that. Okay, now when you have that graph, look at what you've got on each axis here. Okay, distance is going on the x-axis and force is going on the y-axis. That's really important in order for us to get the right units, okay, when we're doing the math that they ask us to do in here. All right, so we'll have it set up that way, and then copy it over into your Google Doc. Now, for the calculations that they're going to ask you to do, to build this graph, which has to be your first column then? When you're in Google Sheets. What goes on the X has to be the first column. So enter distance in column 1, okay, or column A, and then force in column B, and it'll graph it the right way. Right? You will want the equation on here. Not that we're going to use really anything from it, but it's always good to have it on there. So make sure that the equation is on there. We're not actually going to use the slope for anything. It's when we do this kind of again in Physics 20, and we actually use the slope, but not for you guys. So once we've got this graph built, okay, the only two things you have to do is calculate the area beneath the line and tell me what that represents. Okay, so question number 1 is calculate the area underneath the line. Fairly simple calculation, but I'll run over it with you. Okay, and what does the area under the force distance graph represent? How do you know? Okay, when you're looking at this graph, take a look at the two things that you are using to get the area under the graph, and when you're going base times height, what that means. Okay, what might you get from doing that? What are the units? Kind of use that for justification, okay, things like that. Now, when you build the graph in Google Sheets, it's probably not going to come out to having exactly a y-intercept of the origin, okay, meaning your line's not going to start at 0, 0. Is that okay? It's not a big deal. Okay, it's not a big deal. We just might have to do one extra calculation. What we found in period 1 is that most people were getting a y-intercept that was negative. Okay, that means that their line actually went through the x-axis here and then intersected the y-axis down there. So their equation ended up looking like this: y equaled their slope times x minus some small decimal. Okay, so in order to figure out the base of this triangle, okay, you had to do basically two calculations. You had to figure out what x was when y was what? 0, right? Right here, y is 0, agreed? Okay, so that'll tell us what x is, so we can kind of subtract this piece out from the base of our triangle. Okay, and then our maximum force, okay, is 0.12. All right, so we know that all of our graphs are going to end, or sorry, our maximum distance, is 0.12 meters. So whatever 0.12 minus what you get here for x will be the base of your triangle. Everyone follow on that? Okay, to get the height of your triangle, well, you'll have to calculate what y is at 0.1 when x is 0.12, and that'll tell you, okay, what this is. Most of the time, the points were actually right on the line. The graph is really, really linear. Like all of your points essentially fall on the line. If they don't, then you'll have to do that calculation where calculate y when x is 0.12, and then you'll know the height of your triangle as well. Okay, everyone all right with that? Right, so there's a little tiny bit of graphing math to do before you do that area calculation. Once you have the area calculation, question number 2 needs a couple of sentences explanation. All right, it's asking you, what does the area underneath that graph represent? Tell me, okay? Here's the math I did. Here's what I end up getting. Maybe talk about units, stuff like that. That's what should go in there. Okay, and then lastly, you got your conclusion. So restate your hypothesis. To accept or reject it, go back to your reasoning for question number 2. Talk a little bit about that. Okay, I was trying to calculate work. Is that what I really got? Yes or no? Okay, and then for the evaluation, sources of error and how to fix them. Okay, be watching for things that happen during the lab. I'm pretty sure you'll be able to come up with at least 2. Okay, you only need 2, but I'm sure there's more than that. And then don't worry about the class discussion. We will talk about that after I mark the labs and hand them back. Okay, are there any questions on that? Okay, so this is due on Friday, right? The reason for that, you'll probably get it done in class today. If you do and you want me to look it over, let's do that like Tuesday, Wednesday, and Thursday, so that I don't have a lineup of 40 people on Thursday. Okay, if we're all getting it done today, some of us could do that tomorrow. Okay, and we'll spread it out over a few days. Okay. All right, so all the equipment you need is over there on the table. One thing, you do need a spring scale that goes to 2,000 grams. Okay, they say that on the top and on the sides. Make sure that you get one that reads 2,000 grams. The face is red. Okay, if you get one with a green face, you got a 500 gram. That's not what you want. Last thing, in terms of making sure that your measurements are accurate, the little silver thing inside moves. Okay, so you need to make sure that when you start, okay, that the little tab here is actually at 0. So you just pull this thing a little bit, okay, to make sure that it's at 0 when you start. Okay, lab safety stuff. No snapping people with the rubber bands or shooting the rubber bands across the classroom. When you're done with the rubber bands, please put them back in the bag, okay, as long as they haven't been damaged. Secondly, the rulers are not swords, okay? I should see no rulers or meter stick duels during class. Clear? Okay, let's get to it.